This is Chang from Arizona State University, and the work is co-first author with Ziyang, who unfortunately cannot be here today. So I'm going to present TYGR for the field of type inference. Before we dive into type inference, let's first talk about compilation, the process of transforming high-level programming languages, such as C source code, into low-level programming language, like assembly code, which will be later transformed into executable and binaries that can be executed by computer processors. However, during the process of compilation, some high-level information is lost, such as variable names, variable types, control flow structures, and comments. To tackle the information is critical for understanding binaries, and people need to do malware analysis, software debugging, software maintenance. We cannot avoid using those information. To tackle this problem, people developed reverse engineering, the process of transforming those low-level programming language back into high-level programming language. So today's paper is about variable types. It's about recovering variable types. So what is variable type recovery problem? Let's take a look at the source code here. There is one structure type, options, which has two members, one integer type, the other char type, and the function func is just simply assign values to those variables. And the corresponding assembly code is marked as the same color here. We treat the variable type recovery problem as reconstructing the source level types from untyped memory addresses. There are several attempts that people have done to solve this problem. The first one is the constraint-based method. This method involves collecting type constraints to encode data flow information. For example, here, if a variable x is added by some constant, then the variable belongs to some numeric values. After we collecting all the constraints, we need to write rules to solve that. This step usually takes really long time. So people design the machine learning-based method because we don't want to write all those rules. However, the machine learning-based methods implicitly encode the data flow information. So our tool, our intuition here, what if we can explicitly encode the data flow information into graphs? What if we encode the variable access pattern, variable usages? Those access patterns are usually noisy-free for machine learning training. And there's a need to avoid manually write rules. So wow, TYGR comes. Yeah, so that comes. So TYGR consists of two parts: data flow analysis, graph embedding, and to increase the diversity of the data set, we built a new data set. Consists of 5 different architectures. Here's the pipeline for TYGR. First, our input is script binaries. So we fed those script binaries into Anger, and we perform the symbolic execution here to get the data flow analysis. From here, you can see those information, like data access information, are encoded in the graph. The yellow node means the value, the concrete value here, and the edges means the access path, the operations performed on a given location, like has store, add, and move. The red one is the address, like memory address and the register address. The graph will be later embedded into graph neural networks. And from here, we encode the features, like value features, address features for memory location, and register location. And we also encode edges. There are more features we encoded. If you are interested, please take a look at our paper. And the final step is the type prediction. So from here, we recover the concrete type for the memory location, such as the integer type for both RBP-8, RBP-4 location. So we have solved many challenges in our paper. One of them is the type recovery for structure type. Let's still take the same example here, which involves 3 variable types: .flag, .name, and temp. So what are the variable types for them? One existing solution, they are trying to recover the types by size. So from here you can see there is structure with 2 members, size of 4, size of 1. They are trying to recover the types by size. And they will assign the same result to both .flag and .name. For temp is primitive with size of 4. But you can see the problem here. There are many variable types that has the same size. And if there are another structure which has the same shape, they won't be able to tell whether those 2 different structures, those 2 different variables belongs to the same structure or not. And people also are using machine learning to solve these problems. For example, here, this method can provide the result like struct, integer type, char type for the .flag and .name. But that can work only if the structure integer char is in their diction. If in their training set there is no variables has that structured shape, they won't be able to recover that. So how do we do that? How do TYGR do that? We split the problem of type inference for structure type into 2 steps. In the first step, we are trying to recover the basic type, like the primitive type. In this step, we are trying to recover .flag, .name as struct. We are trying to tell whether a given memory location, register location, belongs to a struct or not. And in the second step, we masked all other primitive types away and only kept those member types, structure member types. From here, we recover the concrete type for them, like the integer type for .flag, the char type for .name. So the final output of TYGR would be structure integer type for .flag, structure char type for .name, and integer type, of course, for temp. We have also built the dataset compiled from Gentoo and Debian repository. There are 5 architectures in total, 4 optimization layers. There are more than 300,000 binaries and 100 million functions in TYGR dataset. So, evaluation. We have compared with existing state-of-the-art method. In conclusion, we perform better both on the overall accuracy and structure accuracy on core UTLs or 0 executables. We have also performed the accuracy, the evaluation on accuracy per type on x6400 dataset. And from the result, you can see the more data we have for a given type, the higher accuracy we can achieve for that. That's the trend we can learn from here. However, there is one special case here. For the Boolean type, it only occupies 1.7% of the dataset. However, we achieve comparatively high accuracy here. Why? So we have a conduct investigation on that. We found because the Boolean type is usually used as flag in the program, which resulting in more program paths in the symbolic execution. And when we pass the result into graph, there are more than twice number of edges connected to the Boolean type compared to other nodes, other variable nodes. So that is a very distinct access pattern. We explicitly encode such access pattern into graph, and we believe that is why we perform better compared to other methods. So in conclusion, TYGR, we designed TYGR. The system uses a novel graph-based representation of the data flow information. We have also constructed a dataset that consists of 5 different architectures. All of our models, data, and source code are available on the GitHub. Thanks for joining this talk, and special thanks to my lovely lab mate and Professor being here. If you have any questions, please go ahead.